In this video lecture, I just want to talk about differential equations. What is a differential equation? What is a solution to a differential equation? So this is really just like an introduction to what a differential equation is and what it means for a function to be a solution to a differential equation. So here I have a solution, or not a solution, a differential equation. And really, at the very basic level, a differential equation is just an equation that has a derivative in it, right? So here we have this derivative, y prime. It could include a second derivative. It could include the function itself. So we're looking for y, which is some function of x. We're looking for some function that if I take its derivative and I add to that 2 times the function, then that equals 0. So I'm not going to get into how to solve it. I first want to kind of talk about what does it mean to be a solution to a differential equation. So let's look at the function y equals e to the negative 2x. All right, so I'm just kind of pulling that out of thin air just to kind of demonstrate what it means for a function to be a solution to a differential equation. So don't worry about how I got that right now. We'll talk about that a little bit later. But right now, let's just start with this function and see if it's a solution to this differential equation. Well, y prime, the derivative of that, would be negative 2 e to the negative 2x. All right, just from what we know about taking derivatives of exponential functions. So what I want to do is I want to take this, and I want to put it in here for y prime, and I'm going to take this, and I'm going to put it in here for y. And if it makes the equation equal 0, then it's a solution. So let's go ahead and do that. I've got negative 2 e to the negative 2x plus 2, this 2, times the function, which is e to the negative 2x. And of course, negative 2 e to the negative 2x plus 2 e to the negative 2x, that is 0. So that means that this function is a solution to this differential equation. And in fact, so I'll move over here. If we have y equals c e to the negative 2x, right, where c is any number, right, we can show that that also is a solution to the differential equation. So let's go ahead and show. So y prime is going to be negative 2 times c e to the negative 2x. That's what what I'm putting in for y prime. Here's my y, so I have negative 2 c e to the negative 2x plus 2 times c e to the negative 2x. And again, negative 2c, positive 2c, both of them have e to the negative 2x. Of course, that's going to equal 0. So this is, so just let me kind of highlight this now. So we say y equals e to the negative 2x. We call that a particular solution. And we call y equal c e to the negative 2x a general solution. So in other words, if I let c equal 1, I have this particular solution. I could let c could be anything, but the particular solution fills in a particular value for c, where the general solution has this kind of a general c. So let's give another example of how I could find maybe a different particular solution using this general solution. So suppose we want to find, we know this general solution, we know that that one satisfies this differential equation, but we want to find the solution that passes through a particular point. All right, so let's say through 0, 1. Let's find that particular solution. Well, again, I'm starting with y equals c e to the negative 2x, so I'm going to put in 0 for x, 1 for y. So I'm going to end up with 1 equals c e to the negative 2 times 0, right? So, well, e to any power, or sorry, e to 0 is always 1, right? No matter what else is going on up here. Actually, anything to 0 power is 1. So this means that c equals 1. So this particular solution is the one that passes through this particular point. But there may be a different solution that passes through a different point. So for example, what about the one that passes through, let's look at the point -2, 5. Alright, so again, using this general solution, let's put in 5 for y equals ce to the -2 times -2, putting in -2 for x. Alright, so that equals ce to the 4th, and then if I divide by e to the 4th, I end up with c equals 5e to the -4. So, not a nice number like 1, but this is a different particular solution. I would end up with y equals 5e to the -4 times e to the -2x. That would be my particular solution that passes through this point, -2, 5, where this particular solution passes through a different point, 0, 1. So let's maybe talk about what that means graphically. What do we mean by it passes through a particular point? Why does one of them pass through one point and another one passes through a different point? Well, let's look at a different differential equation here. Let's look at dy dx equals 2x, which we might also see written as y prime equals 2x, or even y prime minus 2x equals 0. These are all equivalent. Some of it's just different notation between dy dx and y prime. From here to here, all we're doing is moving the 2x over, so it looks a little bit different, but it's the same thing. And in this case, it's not hard to figure out. In here, for this example, we haven't learned how to solve a differential equation like this, but this is pretty straightforward, right? I mean, this is just y prime equals 2x. We're looking for a function that if I take the derivative of it equals 2x. So clearly we could just integrate both sides here, right? The antiderivative of y prime is y, and the antiderivative of 2x, well, the derivative of what gives us 2x? Well, that's x squared. But it's not just x squared, it's x squared plus c. So this is, with this c, this constant of integration, this is a general solution. So graphically, what we're looking at is, I could have, like, just y equals x squared plus 0, right? I would have that. That's a particular solution. Another one that would work, I don't know, maybe come down here and call that -5, and we can draw basically the same. So there's a different solution. I could come up here, and I could draw the same parabola up higher. All right. So these are all of this form. This would be x squared plus 0. This would be x squared minus 5. This might be like x squared plus 8. But all of them satisfy this differential equation, because if I take the derivative of any of those functions, so yeah, let's call this x squared plus 8. Let's just call this x squared. Let's call this x squared minus 5. If I take the derivative of any of those, I get 2x. But notice that they pass through different points. I mean, they pass through a lot of points, but this one passes to the point 0, 8. This one passes to the point 0, 0. This one passes to the point 0, -5. So knowing one point that the solution passes through can help us to solve for c and to get us a particular solution. So to demonstrate that, let's look for the particular solution that passes through the point 0, 4. So again, we put in 4 for y, 0 for x. So c equals 4. So y equals x squared plus 4 passes through this point, which was kind of obvious to see from here. This passes through 0, 8, 0, 0, 0, -5. So it's, but I more kind of want to say, kind of coming back to this, maybe look at, well, why do I end up with different particular solutions depending on what point this goes through? I think graphically, hopefully you can see that while the shape is the same, it's always a parabola of the form x squared plus some number, they pass through different points, and all of them satisfy the differential equation. So that's basically the introduction to differential equations, is understanding what it means for a function to be a solution to a differential equation, looking at the difference between a particular solution and a general solution. And we do know, based on just what we know about integration, we can find solutions to some differential equations. If it's just some of the form y prime equals some function, then we can just take the antiderivative of that function to find the solution. once we have a general solution and we need to know a particular point, then we can put that into the general solution and find a particular solution.